Okay, everybody. Where we last left off, we had just finished going over the first three questions, the big three questions on the 2019 pre-response AP exam. So remember, for the free response, the first three questions, each one is worth 10 points. So that's a total of 30 points. Now, the next four questions, question 4, 5, 6, and 7, they're only going to be worth 4 points apiece for a total of 16. The total free response is only 46 points. And remember, those first three questions is where you're going to get the most bang for your buck. All right, so again, College Board recommends you spend about 23 minutes on 20 to 23 minutes on the first three questions each, and then around 8 to 10 minutes on the next four questions, on questions 4, 5, 6, and 7. Remember, they're only worth, like, if you get to question 4 and you look at it, it's only worth 4 points. So get as many of those 4 points as you possibly can, but don't waste time. Okay. So let's jump into question 4. All right. So a student is doing experiments with CO2 gas. Originally, a sample of gas in a rigid container, remember rigid means volume is constant, at 299 Kelvin and 0.7 atmospheres. The student increases the temperature of CO2 gas in the container to 425 Kelvin. Describe the effect of raising the temperature on the motion of CO2 particles. So remember, increasing the temperature increases the average kinetic energy, and that means the average speed, the average velocity, the average speed of the particles is going to increase. All right, so that's what we're doing there. All right, so we want to say an increase in temperature increases the AKE, average kinetic energy. And remember, you can abbreviate certain things on the AP exam. Like, instead of London dispersion forces, you can say LDFs. Instead of intermolecular forces, you can say IMFs. And you can just say AKE, average kinetic energy, if you want to. But it increases the average kinetic energy of the particles, therefore the particles move faster. There we go. That's all you need. That's probably only worth 1 point. Oh, the other thing is we got 4 prompts, so each one is just worth a point. So A is going to be worth a point, B is going to be worth a point, C is going to be worth a point, D is going to be worth a point. That's it. Okay, so try to get 3 out of the 4 if you can, right? So A's number 1 is pretty easy, right? Temperature increases, that means average kinetic energy increases, that means the average speed of the particles increases. So the motion of the particles are going to go up, the average motion. All right. Calculate the pressure of CO2 in the container at 425. So remember, the volume stayed constant, and since this was a contained gas, the number of particles remained constant. So that means the only variable we're dealing with is pressure and temperature. So this is a Gay-Lussac's law question. P1 over T1 equals P2 over T2. I'll stress this. This wasn't an issue this time, but remember, if they had given us degrees Celsius instead of Kelvin, when you plug it into a gas law, you need to be in Kelvin, all right? So we're just solving for P2 here. So it would be 0.7 divided by 299 equals P2 divided by 425, and that's all we need to do. Now, if, let's say for some reason you didn't remember this relationship, P1 over T1 equals P2 over T2. You could use the ideal gas law, but you would have to assume how many moles of gas. So you could assume 1 mole of gas, and you'd have to assume a volume. So assume 1 mole of gas, assume assume 1 mole of gas and assume the volume, and then, or I guess what you would do, never mind. I think the easiest way, the fastest way, if you're going to be using PivNerd, it's going to be kind of difficult to answer this question. All right, but Gay-Lussac's law, so let's see that executed here. So P1 over T1 equals P. See, I was initially thinking PivNerd, solving for the new pressure, okay? But I'd have to make a ratio because I don't know how many moles I have and I don't know what the volume is, right? Again, you could pick one and they would be constant, but this is going to be a lot faster here. So we're just solving for P2, we plug in our numbers, we solve it for P2. Because our P1 was in atmospheres, our P2 is in atmospheres. And understand the pressure should increase. So if you got like a smaller number, you probably did accidentally did P2 divided by 299 instead of P2 divided by 425. All right. So again, that's just 1 point. All right. In terms of kinetic molecular theory, briefly explain why the pressure of CO2 in the container changes as it is heated. All right, so remember, we sped up the particles. The amount of space that the particles occupy is fixed, so they're going to collide more often with the container walls, and they're going to collide with greater force, greater energy. So pressure goes up, right? So, but we got to, when they say kinetic molecular theory, you got to you're describing the motion of the particles. How does that affect the pressure? Okay. So remember, pressure is all about collisions with the surface. So faster moving particles confined to the same volume will collide with the sides of the container more often and with greater force. Therefore, pressure increases. Okay, but you have to talk about the movement of the particles. That's kinetic molecular. All right, you got to talk about kinetic motion and molecular particle. All right, motion of the particles. Okay. And then the student measures the actual pressure of CO2 gas in the container at 425 Kelvin and observes that it's less than the pressure predicted by the ideal gas law. So the pressure is actually lower. So the ideal gas law would tell us, okay, it's going to be 0.99 atmospheres, but it maybe came out to be, 0.87 atmospheres. So it's still increased, but it's not as high as it should be based on the ideal gas law. And that means the gas is deviating from ideal behavior. And remember, the two assumptions we make for an ideal gas are there's no intermolecular forces between the particles, right? Collisions are elastic. And so that means when they collide, they don't stick, right? No intermolecular attractions. And then particle volume is 0. So which of these assumptions that we make for an ideal gas would be in play here to cause us to have a lower pressure? So if particle volume wasn't actually an issue, then we would expect the pressure to be greater because the particles volume take up more space than actually predicted, right? But since pressure was less, it's probably because the particles are sticking together more than we give them credit for. So this would have to be due to the intermolecular forces. So you would say the ideal gas law does not take intermolecular forces into account. The intermolecular attractions between the particles in the actual sample yield less collisions than expected. There you go. The particles are sticking together more than we give them credit for. So they're not colliding as often with the container as we think it should, based on the ideal assumptions. All right. So boom, 1, 2, 3, 4. That's pretty easy there, and not a lot, and it shouldn't take you too much time there. Okay. Remember, you got maybe 10 minutes to budget there. 4 points. All right. Let's move to question 5. All right. All right, so we got a PES. As soon as I see the PES, make sure you check. I've never seen it to be an issue, but notice that this is a higher binding energy than here, so we're going high-low. So this is where your electron configuration would start, and this would be the end. So this would be the valence shell. All right, and real quick, I just annotated it real quick. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. It's not 4s1. If it was 4s1, the peak would only go up to here. All right, but it's 4s2. So we know it's calcium. We check our periodic table, that's calcium. So we've identified the element. We have the electron configuration up there, and I haven't even read a question. And it's real quick. All right, so based on the spectrum, write the ground state electron configuration for the element. All right, I already did. All right. Now notice that they, I think they didn't say full, they just said ground state. So you could do argon in parentheses, brackets. You could put argon in brackets 4s2. You could do the shorthand, the noble gas configuration. So you could have brackets argon 4s2, and that would save you a little bit more time. Not much, but a little bit more. And we've identified the element, calcium. All right, so this one says calculate the wavelength in meters of electromagnetic radiation, light. So calculate the wavelength of light needed to remove an electron from the valence shell. So remember, binding energy is basically the same thing as ionization energy. So first ionization would be equal to the binding energy of an electron in the furthest away energy level. So it would be this. So this is binding energy. Now this is where we have to read the graph. It says binding energy per electron. That's why these numbers are so small, right? 0.9 times 10 to the negative 18 joules, because it's talking about a single electron. Most of the time when you're given binding energies on PES, it's going to be like per mole of electron. So if this was energy per mole of electron, we would have to take that number and divide by Avogadro's number to get energy for a single electron. But because they already did that for us, this is the energy. So this is the energy required to remove an electron. That is the ionization energy. So that's the energy we need our photon to be, okay? So remember, we got this equation on our formula sheet and we got this equation on our formula sheet, E equals h nu and C equals lambda nu. If you quickly combine them, E equals hc over lambda. Remember, h and c are constants, they're on our formula sheet, and lambda is wavelength. That's what we want to find out, right? And so all we have to do is rearrange this equation and say lambda, wavelength, equals Planck's constant times speed of light over the energy, and that's the energy we would plug in. Again, read what the graph is. This is binding energy per electron, not per mole. So again, if this was energy per mole of electrons, we would have to take that number and divide it by Avogadro's number first, and then plug it in. But they already did that for us. So this is just plug in numbers and solve. And we don't have to do anything. Meters, the speed of light you're given on your formula sheet is meters per second. So when you solve for wavelength using the constants given to you on the formula sheet, it will be meters. It will be meters, and you're done. All right, so it's just plug in. Now again, if you don't want to do that, you could just plug in your E, right, which is this, plug that in, plug in the Planck's constant and solve for frequency, and then once you get frequency, plug it in here and solve for lambda, wavelength, or you got that one, right? This is a little bit of a time saver, all right? So we plug in Planck's constant times the speed of light, that's a negative 8, and we put in our energy, make sure we enter it in the calculator properly, and we get 203 nanometers, or 2.03 times 10 to the negative 7 meters. All right, so pretty easy. Now I would say we got 1, 2, 3 prompts. I'm gonna say, B is gonna be worth 2 points. And it's probably 1 point would probably be knowing to use this energy as your energy of ionization. I would say 1 point for, kind of implicitly or showing that that's how much energy would be required to remove one of these electrons, because that's how much energy they're bound to the nucleus by. So if you add that much energy to the electron, it could break free from the nucleus, right? So that's what ionization is. So make sure, kind of like recognizing that, and then 1 point for just correctly executing the calculation. We got a lot of scientific notation. We're dividing by a number in scientific notation. A lot of mistakes show up on the calculator there. So make sure you know how to do that. All right, let's move on to question 6. All right, so real quick, I'm gonna zoom out a little bit. So notice that we're given concentration versus time, 1 over concentration versus time, and natural log versus concentration versus time. Now they gave it to us in a slightly different order than we usually see it, right? Usually it goes 0, 1, 2. So normally it would be concentration versus time, natural log of concentration versus time, 1 over concentration versus time, but they did that on purpose, okay? So right off the bat, before I even read the question, this is the one giving me the straight line, so I know NO2 is second order. Boom, boom, got it. All right. So you got nitrogen dioxide is produced as a byproduct. Well, first, okay, let's break it down. So we got part A, part B, and part C. And so 1, 2, 3, 4. So we got 4 prompts, so we're gonna get, each one is just worth 1 point. All right, so NO2 is produced as a byproduct of combustion of fossil fuels in internal combustion engines, so like when you drive your car. At elevated temperatures, NO2 decomposes according to this equation. The concentration of a sample of NO2 is monitored as it decomposes and recorded on the graph directly below. The two graphs that follow it are derived from the original data. So you got concentration versus time, and then we took 1 over those concentration numbers and plotted that versus time, and then we took the natural log of those numbers versus time and plotted that. Again, that gave me the straight line. I know it's second order. Explain how the graphs indicate the reaction is second order. Okay, so the 1 over concentration versus time had a constant slope. That's telling us that this reactant is second order. All right. So let's see. The graph of 1 over concentration versus time produce a straight line, while graphs of concentration versus time and natural log of concentration versus time do not. This shows second order kinetics. There we go. Boom. All right. Now, okay. Write the differential rate law. So notice that that's the only reactant. So that's the only thing would be included. And it would just be rate equals K times the concentration of NO2 squared because it's second order. Okay. Part C, we got some mechanisms here. It says, consider 2 possible mechanisms for the decomposition reaction. Is the rate law described by mechanism 1, shown below, consistent with the rate law you wrote in part B? So this is our slow step. NO2 shows up twice, so it's second order. So yes, this mechanism works. All right. And then let's look at 2. Is the rate law described by mechanism 2, shown below, consistent with the rate law you wrote in part B? Justify your answer. Here's a slow step, so we're going to use both steps. And NO2 shows up twice. So it's second order. So both of these mechanisms are consistent. Okay, so let's see what we did there. So part 1, yes, it is consistent as it shows 2 particles of NO2 needing to collide before the rate determining step. And number 2, yes, it is consistent for the same reasoning explained in part CI. There you go. So be careful there. I think a lot of students are just gonna, they notice this one is consistent, so they say yes, and then they're gonna make up some reasoning why this might not be consistent, because they don't think they would give you 2 consistent mechanisms. And in this case, they did. So, that's kind of a trap. But again, that would be only worth 1 point. And so if you get 3 out of 4, do well in the multiple choice. You're in really good shape. All right. All right, last question. All right, so we got a redox reaction. We got a burette. I'm thinking redox titration. All right. A student dissolved 0.139 grams of oxalic acid in water in an Erlenmeyer flask. Then the student titrated the oxalic acid solution in the flask with potassium permanganate, which is dark purple in color. The balanced chemical equation for the reaction that occurred during the titration is shown above. Again, we got parts A, B, C, and D, so 4 parts. Each one is worth just 1 point. Identify the species that was reduced in the titration reaction. Okay, so we got to assign oxidation numbers. So manganese is going from +7 here to +2 here, so it's manganese. Bam, we got it. All right. But if you looked at the oxygen, the hydrogen is staying at +1. All the oxygens are staying at -2. So the thing that had to be oxidized is the carbon. But let's see. So if hydrogen's +1, you got 2 of them. That's a total of +2. Oxygen is a total of -8 here. So you got a total. So the carbon has to be a total of +6. So the carbon here is +3. But over here, it's +4. So +3 to +4 is oxidation. Carbon's being oxidized. Manganese is going from +7 to +2. All right, so reduced is the permanganate or the manganese. So you would say manganese in permanganate, or you could say permanganate's reduced, even though it's just the manganese that is. And you want to justify it's going from +7 to +2, which is reduction. All right, so the student used 50 milliliters of the burette to add permanganate to the oxalic acid until faint lavender color was observed. Okay. Remember, as the permanganate gets dissolved, like permanganate's purple, but as it gets consumed, the reaction's still going. So once you add permanganate and the solution stays purple, then you know you've reached the end point of the titration. So they're telling you you've reached the end point of the titration. The initial and final volume readings of the burette are shown. Write down the initial reading and the final reading and determine the volume of potassium permanganate that was added. Remember, don't make this hard, all right? You're gonna get your initial reading and your final reading. Remember, burettes can go to 2 decimal places. If you do not show 2 decimal places, you will not get the point, all right? So read the bottom of the meniscus. 3 is here, 4 is here, so this is 3.1, 3.2, 3.3, and here's 3.4. So this is in between 3.3 and 3.4, okay? This is 29, this is 30, so right there, that line is 29.5, and that line is 29.6, so we're in between 29.5 and 29.6, but you need an estimated digit, you need the hundredths place, right? So these were my measurements, 3.36 for the initial, 29.56 for the final. If you don't have an estimated digit, your estimated digit can be different from mine, that's fine, okay? But just make sure you have it. If you just said 3.3 and 3.5 or 3.6 or whatever, or if you just said 3 and 29, you're way off. All right, so all we have to do, so those are our 2, that's my initial volume, my final volume, and final minus initial is how much I've added. So in this case, 26.20. Be careful. A lot of kids pick, you know, when I give this was on one of our unit tests, if I give this 29, or I think it was on, you know, one of your assessments, I gave you 29.56. A lot of kids get 29.56 and they get 3.36. And when they subtract, in their calculator, it says 26.2. But when you subtract measurements, you're allowed to limit yourself to decimal places, not about significant figures. So yes, this only has 3 sig figs and this has 4, but when you subtract, it's not about sig figs, it's about decimal places. 2 decimal places, 2 decimal places, I'm allowed 2 decimal places. So if you don't have that 0, you're not gonna get that point, right? And you'd have to have this, a correct measurement here, and that correct measurement to get the point, all right? And it's only worth 1 point because there's still part C and part D, all right? So given the concentration of permanganate was 0.0235 molar, calculate the number of moles of permanganate ions used. So this is just liters times molarity, and there's 1 permanganate ion for every 1 potassium permanganate. So the volume we just calculated here, that 26.20, convert it to liters, multiply by the molarity, and you're done, all right? So I would say 0.02620 liters times 0.0235 moles per liter. If you wanted to show, maybe say 1 mole of permanganate for every 1 mole of potassium permanganate, and you would get it. Now here's where you want to be careful. Notice, like I went right into the mole ratio because I was ready to treat this like a solutions titration question. And the purpose of the titration was to figure out the molarity of the oxalic acid, but none of the questions ask about that, all right? Remember, this is one of those questions that's only a 10-minute long question maybe, and so they might not go the full way. And in your mind, you're thinking, oh, this is redox titration, let me figure out, the whole purpose of this experiment is to figure out, you know, how, the concentration of the oxalic acid solution, but none of the questions ask that. So like here, like this is wasting time. Like I just started to do it and I was like, wait a minute, it's just asking for moles of permanganate. I don't need to worry about that, all right? Okay, and then here, you might recognize this from one of your unit tests, probably unit 2. The student proposes to perform another titration using 0.139 gram sample, so the same mass of oxalic acid, but this time using a much lower concentration. Notice this is 0.001, and in the initial one you did 0.02, all right? And it says, would the titration concentration be reasonable choice if you had the same equipment? And the answer is no, because if you use this concentration, it's going to take much more than 50 milliliters, and the maximum amount this can hold is 50. All right, so it's going to take a lot more. So that would be the justification, but you could do a quick calculation, right? So it would require the same number of moles as part C because we started with the same mass of oxalic acid. So if we take our moles that we got from part C and divide it by the new molarity, that would give us the volume needed. So we would need 431 milliliters of our potassium permanganate solution to react with the same amount of oxalic acid, and our burette only holds 50. So no, it's not going to be a reasonable setup. Okay? All right, so that's the test, man. That's the test. So hopefully, we went through a full multiple choice. We went through a full free response. Hopefully you've taken the time to look at those release free response questions from the past 3 AP exams, so you feel a little bit better. Like, that's the style of question you're going to see on Monday. That's what you should get used to. The international practice exams are good practice, but they're a little bit different. They're just, worded differently. They're structured a little bit differently. And there's a couple concepts that they do that we don't do, and there's a couple concepts that we do that they don't do. So that's why the exams are a little bit different. So you might find them a little bit more difficult, but hopefully looking at this stuff maybe gives you a little bit more of a confidence boost when you're taking the actual AP exam. All right. So anyway, good luck with your final, and good luck with that AP exam on Monday. All right.